All right. Okay, thank you for coming. I really appreciate you being here on another rainy class day. An announcement. So the department sponsors a tech club that is also in the process of becoming an actual club. Um, there's going to be a table at the club fair on Friday. Let me see if I got those details right. Friday, 1 to 3 in Dryden, which is right next to the dining hall. So if you want to stop by, write your email down. We're planning on having meetings once a month. And in those meetings, we'll do something like leet code problems where you can practice for interviews type thing. Um, also, just like being together with other computer science students is sometimes really helpful. And we have some plans in the works. We're gonna try and get together like a mini hackathon this semester at some point, and maybe having some like guest speakers, panelists, former students come and talk with you guys. So if that sounds interesting to you, then come to the tech club meeting. We're planning on having a meeting next Tuesday at 5:30 p.m. I'm still working on the location, but keep that in your brain. Once I have that, I'll let you know on Tuesday. My plan for today, we're gonna hopefully finish the math background packet, just to ease you into this. Um, we'll go over some packet problems. I'll probably have you write them on the board. And depending on how far we get, we might start chapter 2. My plan for chapter 2 is if you have the textbook, then we're going to go pretty much through the definitions of the textbook. And you may have noticed also that there's like practice problems interspersed in the text. Those will be our packet. So I've got some things printed out for you. So if you don't have the book, that's okay. But we may not go through everything in the book. So as always, if you want more detail, then I recommend purchasing the textbook. Um, so the way that we're going to go through at least chapter 2 and probably the chapters going forward is we're not necessarily going to have a slide deck. I might come up with one. But I think, in math classes, how the teacher just like gets up and starts writing on the board. That's the plan. Because that's the easiest format for something that's more math heavy like this. Okay, so let's pull up this and where do we leave off? Okay, so we talked about sets, right? Of what is a set? What's it mean for something to be in a set? Talking about elements. Talked about the empty set. And I think that might have been as far as we got in this class. Oh, we talked about subsets and the power set. We talked about union, where we can combine, if we've got one set and another set, we can just say, yes, I want all of these things. And just like if we've got two bags of things, then just dump them all into one giant bag, and then that's the things in both sets. We talked a little bit about minus, where if we have something that we want to remove, we can do a set minus to take something out. And then I don't think we got to intersection. So this is where we will resume. Okay, so in terms of intersection, intersection is concerned with finding only the common elements in both of the sets. So if I've got my set of, let's see, we were working with fruit last time. So like cherry, banana, apple, and kiwi. And if I've got another bag of fruit that's got a banana, an apple, an orange, and what's another different fruit? Say that again. Pair. Yeah. So if these are my two sets where, and I want to find what elements are in common, then it's the banana and apple, right? Those are the only things that both sets have. Again, there's no restriction on if A or B needs to have any elements. And this is equivalent to the logical AND operator. So only AND is only true if both the first thing and the second thing are true. Yeah, so the union and intersection operators kind of provide this, they facilitate this transition to talking from sets to talking about logical operators. The complement is basically anything but. So you'll see it written as like the set name and then a little C up top as a superscript, or maybe as a prime. Prime is just like a single quotation mark. And that's, yeah. In order to talk about complement, we also have to talk about the universe. So if the definition of the complement of a set A is everything but the set of things in A, we have to talk about what everything but means. And so typically we'll have a universe of these are all of the things that we care about in this context. So for example, let's see, the problem 3 on the packet is we have A equals 1, 3, and 5. And B is equal to 1, 2, and 4. And in this case, we define the universe to be the numbers 1 through 20, right? Because if we say the complement of A, then it gets into infinity except for these 3 numbers. But if we said the universe is just 1 through 20, then we're restricted a little bit. Okay, so the problem 5 on the packet shows you kind of how we can combine these things. So let's start with, I'll show you the A union B complement. So if we look at if this is A and this is B, we know what A union B is, right? Where we color in both A and B. And then the complement is anything but that. So what should I color in here? Someone who's not in 374, go for it. Yeah. So if the box means the universe, we're coloring everything outside the box, but still in the universe. Let's look at, so part of this is also because packets are your homework. Let's look at the 1, 2, 3, 4th one, which is A union B intersect C complement. So first of all, how should I draw A, B, and C? So something like this, maybe. Something that, so if we draw it like this, there's an implicit assumption here. And that assumption is that if this is A, the middle is B, and the right is C, the assumption is that A and C are disjoint. So the way we can write that with set theory is A intersect C is the empty set, meaning there's nothing in common with these two. We've drawn them completely separate, no overlap. And that's fine if we know that A and C are disjoint. But since we're working with just general sets, we don't necessarily have that as a guarantee. So the way I would recommend drawing it for now is 3 overlapping circles. Okay, so how do we approach this? First of all, what's B intersect C? If this is A, this is B, C. B intersects C is this part, right? And so it's saying everything but that. So everything but that little intersection. And then what? There's one more part of this equation, right? The A. So because A is union with it, now we have to color in that a little bit. Does that make sense? And that's how we get everything except for this small little portion. Okay, so I'll leave the rest of those for your homework. And then we get into some Boolean statements. So you've all taken programming 1 and programming 2. So you know the Boolean statement is something that's either true or false. It's a binary calculation. So like the sky is blue today, I would say false because it's rainy. It will rain tomorrow. I don't know. I haven't looked at the weather, maybe. But it's going to be either true or false based on the outcome of the weather tomorrow. And so we also need to know something about Boolean operators, where you know things like and, you know or, and you know not of like P and Q are true if both P and Q is true. P or Q is true if at least one of them is true. The others are, if both of them is true, great, but we only need one of them. There's some other, has anybody heard of logic gates? Kind of. I think if you take like a computer systems class, they'll talk about logic gates where these plus these equal pretty much anything you can make in a computer. So you can build up to something like an if statement or a for loop using just these operations, which I think is really cool. In terms of the ones that you may have not seen, it's not super important for you to know, but I just want to like mention it that it's a possibility. There's operators like NAND, which is true only unless like only until both A and B are true, and then it switches to false. NOR is only true if neither A or B is true. So if only if A and B are false is NOR true. XOR is a common one because you know if you go to a party and you ask, do you want cake or ice cream? And then the person will generally respond, oh yeah, I want cake, or no, I want ice cream. But in terms of the Boolean logic, saying yes, I would like both is an acceptable response in that situation, right? I would like both cake and ice cream. And that's that's fine under or. But if we want to have that exclusivity, we need to use something called XOR, which is true if exactly one of those are true. And then XNOR is true only if both A and B have the same value. So only if they're both true or they're both false is it true. This is a fun graphic that I like to bring up, where we can see all the logical operators in terms of a pumpkin. That's mostly just there for fun. The truth tables, I think I will let you fill in. It's fairly straightforward. If you get confused, it's also like on Wikipedia. Just to give you practice in what are these Boolean operators. But the thing that is really important for this class is proofs, where a proof is something where point A is, we're trying to get from point A to point B. We're trying to tell a story in order to do that. Where in this class, point A is going to be the assumptions that we have going into it, and point B is the thing that we're trying to prove. And so we want to be able to tell a story to get from A to B in a way that the reader can understand each step. So we're going to take individual steps and say, I start from here, now I go here, now I go here, and therefore we've reached our conclusion. So some things you should know for the baby proofs that I have over in the packet. We'll typically work with a variable, so like X or N or K or something. The name of the variable doesn't matter. But typically we assume that it's an integer going into it. If you ever see 2n in a proof, that means that it's an even number because it's multiplied by 2. Therefore, it's divisible by 2, and so it's even. But 2n plus 1 is an odd number, where if you think about it, like 2 is an even number, and then 3 is an odd number, but it's just an even number plus 1, right? Because we know odd numbers and even numbers alternate. That's just how they work. So 2n plus 1, when you see that, you know, oh, that's an odd number. Okay, so I'm going to walk through the proof where we want to show that the sum of two even numbers is even. So I've got an even number, 2a. I know it's even because it's divisible by 2. I've got an even number, 2b. I know that's divisible because it's got a 2 there. A and B are both integers. Remember, this is the in notation, and this fancy z is just, it means the set of all integers. Okay, so we want to prove that the sum of these two numbers is even. So let's add them together. 2a and 2b. That's fine and great. But we want to prove that these two together is even. So what do you think we should do? Because we don't know anything about A and B, right? So here's where like algebra come in. When you see proofs, especially proofs with numbers, there's a lot of like factoring and foiling and playing with the equations that you have. So the way that we solve this is we factor out the 2, which seems to like not really have done anything, but it did, because now we can definitely say that this number is divisible by 2. And therefore, since these two expressions are equivalent, we can say that the sum of these two numbers is even. So the way I would write this, so if this is a question on an exam, I would say 2a plus 2b, or we want to show that 2a plus 2b is even. Then since it's fairly simple, I would say we factor, and so then we get 2 times a plus b, which is even. And then we typically end proofs with either a little square or the letters QED, which stands for something in Latin that I don't remember at the moment. And so that's it. That's what I would expect you to write on a test. So we've still got these 2 steps, and then just add in some words to show me that you know what we're doing. Oh, I wrote it out. Oops. We want to show 2a plus 2b is even. So a statement of this is where we're trying to go. We know 2a and 2b are both even. That's one of our assumptions. That's incorrect. That's not how factoring works. Sorry, that's my mistake. It's still incorrect. But the idea, we got there eventually in both cases, where it's 2 times something. In this case, it's 2 times just a plus b, and not 2a plus 2b. Okay, so that's, I will park it here, and then I had 7. So one of the ones that I would like you to work on, I will, if you want to come take a marker and put it up on the board. The third one of problem 7, which is prove that the sum of any 3 consecutive integers is always divisible by 3. And yeah, I want you to think about it for a moment. If you're stuck, I have some hints. But struggling is part of learning proofs. Okay, you can get in groups if you want to talk about it. But I'll come around and give you markers. I'll let you back at the end. Yeah, that's pretty much it. Were you thinking of adding something else? Yeah. Okay, let's write that out on, nope, nope. I want to add another slide here. Okay, so I think people who put it up on the board, great. For me, I know so I was making this packet and then it was the late afternoon and I was trying to like, how can I prove that the sum of three consecutive integers is divisible by three? I don't know how to do that. So if that ever happens to you, I recommend maybe take a break, go and do something else, and then you can come back to it. Because I came back to it in the morning and I'm like, oh yeah, obviously this is how you do it. So if that ever happens to you, you're definitely not alone. So if you get stuck on something like this, you guys got it on the board. But I want to go through like what happens if you're stuck on something. So the first thing I would try is make sure that it works for the examples. So I gave 1, 2, 3. 1 plus 2 is 3 plus 3 is 6. That's divisible by 3. 3, 4, 5. 3 plus 4 is 7. 7 plus 5 is 4. No, wait. It's 4 divisible by 4, which is 12. Yeah, mental math. And so 12 is divisible by 3. And so that's how so for those first two examples, it works. And so then the next step is to abstract it a little bit. So if it works for these concrete examples, how can we write like the first number in this sequence? So since we like writing things in terms of n, I would say start with n. And then once you are able to do that first abstraction, then you know that, oh, the next number is just n plus 1. The one after that is n plus 1, which is n plus 2, right? So we've gone 3 steps, and these are our 3 consecutive integers. And then from there, you add them together, and then it's just algebra. Right? We've got 3 n's, so we write 3n plus 1 plus 2, which is 3. And then similar to how we knew that 2a plus 2b was even because we could factor out 2, both of these terms have a factor of 3. So we can pull out to get n plus 1. And since there's a 3 there, we can say this is divisible by 3. Yeah. So to write it like on an exam, I would probably say express the numbers in terms of n plus n, n plus 1, and n plus 2, where this is your abstraction step. So going from the problem prompt to here's where we start. So we express it in these terms. And then I would say, that's terrible D, adding together, we get n plus n plus 1 plus n plus 2, which is 3n plus 3. And then I would say factoring, we get 3 times n plus 1, which is divisible by 3. And we're done. So there is the bit of showing your work back from algebra and then adding some words in there. Yeah.
It's probably a dumb question, but what's factoring?
Factoring, not a dumb question. It's been a while, hasn't it? Yeah, so I don't know that I've ever, it's also like been a while since I took algebra, so I don't remember how my teacher explained it. The way I would describe it is like you identify, so like both of these have 3 times something, right? And so the process of going from this step, 3n plus 3, to where we've pulled the 3 out and it said it in the parentheses is 3 times parentheses n plus 1. That process to go from one to the other is factoring. Does anybody else have a way to explain it?
Find a common factor amongst all the numbers or whatever you have. And then divide out that factor, and then to keep it the same, like equal to itself, you have to multiply by.
But yeah, it's also hard to talk about factoring without mentioning like the word factor too. Let's see. Maybe if we have, I'm gonna make something up on the spot. Um, um, Somebody check if 504 is divisible by 4. It is? 64. A. Let's say this is our long and complicated expression. We know that 4a is here, 504 is divisible by 4, and we've got an a here. Even if it's an a squared or maybe a cubed or something. And then there's a 4a also in here. So we can pull that out right at the beginning. And then we can say 4a x to the 5th plus whatever that number is, a log y plus, my mental math is not great. Does anybody know what those numbers are? 26. Thank you, I appreciate that. Yeah, so since 4a is contained in all of those terms, we can just pull it out. Does that make sense?
I think so.
Okay. I know the STEM Center, they may have passed, but they have like math refresher workshops. And if like you're getting into this and you're like, I need a review, I would refer you to the STEM Center, and also there's like videos online, like Khan Academy and stuff. Because it has been a while since algebra. Okay, any other questions? Especially stupid questions? I love stupid questions. Those are my favorite. Okay, seeing none, let's move on. Okay, so the rest of problem 7, I'll let you do on your own. I think the weekday one, that's fun. For problem 8, there's 4 main kinds of proofs. One is the example that we just did, direct, which is where we start from somewhere and we go to somewhere, and it's like no fuss, where we have one step, then another step, then we get to the end. That's what we call a direct proof, because we go directly from A to B. Kind of flip side of that is what we call contrapositive. That is the equivalent to not B implies not A. That's also something from Boolean logic. But it's called the contrapositive because that's what this expression means. So the way that it works is we assume that the thing we're trying to prove is not true. So like, or if we can write it as A implies B, then we assume B is not true, and then we work our way to not A. This is also fairly similar to a style called proof by contradiction, but it's a little bit different. So let's say contrapositive is, so if we said 2A plus 2B implies 2A and 2B implies 2A plus 2B is even. Then we said, assume this is not true, and then we get to that 2A and 2B, but A and B aren't even. So, yeah, so the contradiction is a little bit different, where we're saying that this whole presumption of A implies B is false. So this whole statement is false, and then we have to kind of work our way towards breaking the assumptions. So do I have? I do have one. Okay, so we'll go through the other styles, and then we'll look at an example for contradiction. Induction is the process where, if you remember recursion, it's a similar kind of deal where in recursion, we have a base case, which is the simplest possible way we can solve this problem. And then we say, let's assume it works up to some value, and then we'll look at one more than that. We'll see an example. First, let's look at contradiction. So we're going to look at a very famous example of a contradiction proof, which is that we want to show that the square root of 2 is irrational, right? Something to know is that rational numbers mean that we can write them like as a fraction, right? And so we can write it as P over, not P over P, P over Q, where we say both of these are integers, and we say that they're not both even. So rational numbers, we can write them as one integer over another, and they're not both even. Not both even is important because if we had like 4 over 2, we can reduce that, right? That reduces, if we write it in fraction form, 2 over 1, right? But if we have something like 3 over 4, we can't reduce that further because there's no common factors. So we just assume that they're not both even. So the contradiction step is take our statement here and just be like, no, let's just assume that it is. Assume that it is, and then we can write it like this. We can write square root of 2 is equal to P over Q. We can say there's some fraction of numbers that we can write square root of 2 as. And then we just do some math and try and figure it out. So if we have the square root of 2 is equal to P over Q, let's square both sides, see what happens. So then we get 2 equals P squared over Q squared. And then let's try moving Q squared to the other side. And so we get 2Q squared is equal to P squared. This tells us something about P squared. What does it tell us? It's even. because when we have 2 times something, then it's even. So p squared is even. And then something that's one of the proving things. It's not quite, so I have proved that the square of an odd number is odd. You can similarly prove that the square of an even number is even. So that's how we know that p is even. If you want to prove that for yourself, I'll leave that as an exercise. So once we know that p is even, we can write it as some integer. So p is even, which means it's equal to 2 times something. That's what an even number looks like. So k is just some integer. We don't care. It's just an integer. Wait. Does anybody need more time to write it down? Okay. So p is even. We can write p as 2 something. So if we've got 2q squared is equal to p squared, we'll replace p with this even number. And then we get, since to square something in here, we square both of these, and so it's 4k squared. And so since last time we tried isolating p, now let's try isolating q. And so if we divide both sides by 2, then we get q squared is equal to 4 divided by 2 is just 2k squared. What does this tell us about q? It's even too, right? So q squared is even, so q is even. What's the problem with that? Yeah. Right. Yeah, all the way back here, we said they're not both even. That's the thing where we've worked with our assumption up until we get to a point where our assumption has been contradicted. And so because of that, now it allows us to say that the square root of 2 must be irrational. Okay, let me look at this. So the one I would like you to try and write on the board is 9b, which is 0 is an even number. So try and prove it by contradiction. Let me draw what you have over there so far. So keep going, keep going. So you start off with 0 is not even, which means because it's a parity, right? A number is either even or it's odd. Two options. So if 0 is not even, then it's got to be odd. And the way we write an odd number is 2 times something plus 1. And so, yeah, so you subtract 1 from both sides, and then divide by 2. So we get n over here is equal to what? Yeah, -1/2. And then what do you have? Where do we go from here? We could plug it back in if we wanted to, but then we would get 0 equals -1/2 times 2 plus 1, which is -1 plus 1, which is 0. So we're kind of at an impasse, right? Except we aren't. There's an assumption here that I believe we've forgotten. What do we assume it means to express an odd number? Let's go back to the slides. We assume that to write an even number or an odd number, we write it as 2 times some variable, where that variable is an integer. What's our problem here? Yeah. Yeah. -1/2 isn't a whole number. It's a fraction. And so once we get here, why has it stopped writing? Once we get here, that's our point of contradiction, where we say -1/2, that's not an integer. So contradiction. Therefore, 0 has to be even. So this is something to always remember. What are you assuming going into this? And if you go back to your assumptions and you examine them again, you'll probably see this is where that sticking point is. The idea is that as we traverse through the proof, we need to always keep in mind, what do we know? And then what can we say at this next immediate step? Okay. 11b, can we do 11b? No, not yet. Okay, we did that. Induction involves a similar line of reasoning. So I will say that proof by contradiction is very helpful for graph theorems, where we're trying to prove a property that holds for all these possible graphs. And sometimes that's it, we can't do that directly, where it's really hard to enumerate all possibilities and then prove that directly. Sometimes it's easier to take the statement we're trying to prove and just be like, no, and then examine the fallout from that assumption. Induction can also be helpful if we are trying to show some general property about a kind of graph. It's a line of reasoning that's very helpful if you don't know how big something is. Yeah, so that involves like, what's the size of the graph? I don't know, but we're going to show that it works for all of those possible instances. So the basic idea with an induction proof is we start really simple, start with a base case and show that it works. Then we assume that it works for some finite number. So some number down the line, we don't necessarily specify here's what it is or not. We say up to there, let's assume that it works. And then we want to show just that additional step, show that it works for one step more. And then that's it, we're done. So I don't think I included that. So I will. Have you learned what? Nope. The pen stopped. Remember what this means? Okay. I think you learned this in like Calc 2 roundabout. So if you haven't taken Calc 2, let me just say that this symbol basically means adding a bunch of things. So if I want to do, let's do 1 plus 2 plus 3 plus 4, and I want to know what's that sum. I can make this as long as I want, right? I can keep adding consecutive numbers one after the other. And so I can say this stops maybe at n. The way to express something like this is to use this guy that looks like a weird E that is, in fact, a capital sigma. It's a Greek letter. And we can assign things around this Greek letter that tells us all about this thing. So if I write my sigma, the thing on the bottom is going to be where we start. The thing on the top is going to be where we end. And the thing to the right of it is like, we're going to express in general, what are we adding? And so the way that we express this thing of 1 plus 2 plus 3 and so on is we start at where? Where do we start counting? 1, right? Yeah, that's the first number. So we start at 1, and then where do we end? I mean, maybe technically infinity, but in this case, we'll just say we stop at n. And then we're adding each individual number, right? So the way we express this is I. And so we'll start at I equals 1. It's the math version of writing a for loop, where if we said for I in range n, I don't know what n is, but I assume I will once I get here. And then if we have the sum, maybe we start the sum at 0, we say sum plus equals I, right? This looks familiar. We're doing the same thing. So we can write it either as a for loop, or we can write it in this nice and tidy little expression. And so the idea with this is that this equals something. And so I would like to prove that the sum of numbers from 1 to n is equal to n times n minus 1 over 2. So I know that's true because I've proved it many times. But I would like you to know that it's true. And we're going to prove this by induction. So as a result, this sum variable expressed in terms of n is going to be n times n minus 1 over 2. Let me add another slide. We have time. We have 5 minutes. Let's do our best. No, 10 minutes. Class ends at 11:20. Okay. Great, we've got time. Okay, so we want to show that the sum of numbers from 1 to n is equal to n times n minus 1 over 2. So the way we do this by induction is we start with a base case, where base case is the simplest possible way. So if I is 0, the sum of 0 numbers up to 0 is, or if n equals 0, the sum is just 0, right? We're not adding anything. If it's 1, the sum of 1 numbers is just 1. We can keep proving, we can say like 2 numbers is 1 plus 2, which is 3. And so if we say if n 0 times 0 minus 1 over 2, this is just automatically going to be 0 because we've got 0 multiplied there. 1 is 1 times 1 minus 1. Wait. Did I get this wrong? I did get it wrong. It's n plus 1. So this is how I know, because I'm trying the base case and the base case isn't working. So it's supposed to be n plus 1. This gives us 2 over 2, which is 1, right? Trying the n equals 2. 2 times 2 plus 2 over 2. This gives us 2 times, or 2 plus 1. 2 times 3 over 2. This is 6. 6 divided by 2 is 3. Check. Are we convinced the base case works? Okay, so the way we could do this is we could prove, if we wanted to do this directly, we could prove it for every possible n up to infinity. But the only problem is we're never going to get there. So the way to do this is to prove by induction. So this is our base case. We're reasonably confident that the base case works. Now it involves the induction hypothesis, where we say, let's assume it works up to some finite number we'll call k. We can call it anything we want except for n. So assume it works up to this number. And then the induction step that we call it is we want to show it works for k plus 1. So assuming it works up to k, that means that 1 plus 2 plus 3 plus so on and so forth up to k is going to equal k times k plus 1 over 2. That's what we're assuming. And then we want to show that k plus 1 works. So let me add another slide. So That's what we assume. So now let's say we're looking at 1 plus 2 plus so on plus k plus 1. Right? We're trying to show that this is equal to that. We know what that is, right? By our hypothesis, we've said that it's equal to this. So we can just stick that right there and say that k times k plus 1 over 2 plus k plus 1 is something. So let's do the math, do the algebra, work it out. So if we want both of these on the same denominator, we can multiply this guy by 2 over 2. Then we get k times k plus 1 plus 2k plus 2, or over 2, right? So we've now brought this guy into the fraction world. We can factor the 2 out, or if we didn't want it to distribute it in the first place. K plus 1, 2 times k plus 1. And, oh look, now we've got a k and a 2. And both of those are multiplied by k plus 1. So we can pull the k plus 1 factor out. So we can say k plus 1, we've pulled that out. And then we've got k plus 2 all over 2. This is actually the answer. To further convince you, remember we're looking for k plus 1, like as a unit. So k plus 1 times k plus 1 plus 1 over 2. That's what we're going for. And so once we get here, that we show that we've reached this formula on the right-hand side that's equal to this sort of formula, now we're done. We've done it. We've proved it by induction. Okay. I want to go through a silly example that I think I drew as a student and is up in the math lounge over in Galileo. Where if we want to invite someone into our house by induction, we start with the base case, right? Your feet clearly fit on the floor. And then the induction hypothesis is, let's assume that you're somehow n feet tall and that you can fit through the doorway, no problem. Since the dining room is, if we're eating in the dining room, then if you're n plus 1 feet tall, you could just like crouch a little until you get into the dining room. Therefore, however tall you are, you can come in. So it's a silly way of thinking about it, but the idea is you start with the base case. You assume it works for some number, then you prove one number after that. That's the process of induction. We've got 2 minutes left. So I think I'm going to 11B, that's the any amount of money. But we don't really have time for that currently. So maybe trying to decide. We may go over 11B on Tuesday, just briefly. I'll make the packet due on Thursday next week. Wait, no. Because your other homework is due next Thursday. Okay. So I'll give you another class period. So the packet will be due on the 25th. So you'll have a little bit more time. So we'll go over 11B on Tuesday, and then we're off to the races with chapter 2 graphs. Make sure you bring like pencil and paper or tablet and pen to write on Tuesday, because we'll transition into that style of lecture. Thank you for coming. I will see you on Tuesday. Stay dry.